All right, so today what we're looking at is the apparent motions of the sun. All right. Now, when you look at the sun's movement, what you notice about it over the course of the year is the sun's apparent path varies with the season. So, where the sun is in the sky in like June is different from where the sun is in the sky in like December. You may notice, like for example, on a ride into school, that there may be days where you're staring right into the sun as you're going to school, but that probably only lasts for a few days. And like the next week, you're taking the same route the same day, and the sun's not in your eyes anymore. It's because the sun's path has changed since then. So the sun's apparent daily path varies with the season. And that's what this shows you right here, is that these are the various paths the sun takes at different times of the year. So the path it takes in June is very different from the path it takes in December or in the spring and fall. All right? So it gets to different heights in the sky, the setting where it rises and sets is different, and so forth. B, the sun's apparent daily path is an arc. So if you look at the sun during the course of the day, the sun looks pretty much the same size, and it moves across the sky, it appears to move across the sky like that. So it looks like it's almost on some track that has an arc in the sky, and the sun's just kind of moving along that track from one spot to the next. Well, if you remember, what people initially thought was that there was this celestial sphere and the sun was actually moving on an arc on that celestial sphere. That's what people initially thought. Now we know that's not the case today. That's what it's really doing, but it's still a convenient model to show how the sun appears to move across the sky. So we're going to use this diagram here of the celestial sphere to show how the sun moves, because it's just convenient to do so. Now, in that arc, noon is when the sun reaches its highest point in its path. So there's noon in December, there's noon in spring and fall, there's noon in June. But it doesn't matter. This diagram here represents New York State. All right, so a place about 42, 43 degrees north latitude. It doesn't matter what season. For an observer right there, he would have to look directly south to see the sun at noon. So the sun is due south at noon. Now, besides the fact it's directly south at noon, if you look at this, what you also notice is that the sun is primarily in the southern half of the sky throughout the year, with the exception of sunrise and sunset in the summertime. The rest of the time, the sun's in the southern half of the sky. So that's why, like for example, this particular classroom I have, I never get direct sunlight in this classroom because my classroom faces north. And as you can see, like the sun doesn't, in New York State, the sun doesn't get in the northern part of the sky. So I never get direct sunlight in my classroom. If my classroom's on the other side of the building, they get direct sunlight all the time in there. You may have heard of the expression, moss grows on the north side of a tree. Well, the reason why that's sort of true is for this, because the sun is in the southern half of the sky. So that means if I have a tree, if the sun's in the southern half, that means the northern half of the tree is the side that's going to be shady. And moss is a type of plant that doesn't like being in direct sunlight. It prefers being in the shade. So that's why you're more likely to find moss on the northern side of the tree. Now I say that that's sort of true because that's really only true if you have trees that are kind of like out in the middle of nowhere. If you go in the forest where there's lots and lots of trees and lots of shade, then really the moss can grow anywhere. But if I have like a single tree out there, the south side of the tree would be the sunny side and the north side would be the shady side, and that's where you're more likely going to find the moss. All right, the noontime position of the sun is never directly overhead, north of 23.5 degrees north, never overhead in New York. So if you look, sometimes if I ask like people like, when is scientifically noon? They might be like, noon is when the sun's directly overhead. Well, if that was the case, then that would mean that New York never has noon, because in New York, the sun never hits directly overhead. Again, this diagram here represents this diagram here represents New York State. And I can see that there's noon in the winter, spring and fall, and summertime. And at none of those times does it get to the zenith, the spot that's directly overhead. The only places on the earth where the sun never gets directly overhead is if you're near the equator. So between 23.5 degrees north and 23.5 degrees south, that's where the sun could be directly overhead. So here's the equator, here's 23 north, here's 23 south. So, and the first day of spring, in March, the sun's directly overhead there, and then in April, it'll be overhead there, in May, it'll be overhead there, in June, it'd be directly overhead at 23 north, and then July be overhead there, August, September be overhead at the equator again, then October, November, December, it'd be directly overhead at 23.5 degrees south, and then January, February, March overhead at the equator again, April, May, June, July, August, September, October, November, December. So it's only directly overhead if you're near the equator, and even then, it's only twice a year. And then if you're 23 north of 23 south, it's overhead just one day a year. Any place up here above 23 north, and any place down here below 23 south, the sun never gets directly overhead. All right, the points of sunrise and sunset vary with the season. So you may normally think that the sun rises in the east and sets in the west. That's actually only true a couple days of the year. First day of spring, first day of fall. The other days of the year, the sun rises in the northeast and sets in the northwest, or rises in the southeast and sets in the southwest. Again, looking back at this diagram here, in the winter months, it rises in the southeast and sets in the southwest. In the summer months, it rises in the northeast and sets in the northwest. It's just on the first day of spring, first day of fall, does it rise directly in the east and sets directly in the west. So the points of sunrise and sunset vary with the season. Now, like right here, this is where sun rises on December 21st. Every single day, it's going to be a slightly different spot. So like on the 21st, it'd be rising right there. On the 22nd, 23rd, 24th, 25th, 26th, 27th, 28th, 29th, 30th, and so forth. So every day where it rises is going to be in a slightly different spot until you get to June 21st. And then once you get to June 22nd, it's going to start rising back this way every day. It's going to start moving back that way. Where the sun rises and where the sun sets is how a lot of early calendars were developed. And probably the most famous of the early calendars was the one that kind of looks like that. That's supposed to be Stonehenge. All right, Stonehenge is basically a calendar. So like various rocks are lined up for when in the first day of summer and first day of winter, the rocks are lined up for a certain way, so they know when those days are. So that way they know precisely, when to plant certain crops or when to start preparing for the winter and stuff like that. So what they used was the differences of where the sunrise and sunsets relative to these rocks to figure out what time of year it was. So a lot of the early calendars, and there's a lot of henges. Stonehenge is the most famous one, but there are a lot of other ones that are made out of wood and stuff like that in in England and in other places in Europe. It's just, that's the one that lasted the best. All right, next. The length of day and night varies with the season. All right, so these dates here are dates that you're going to have to memorize for earth signs. All right, the summer solstice is the day that we get the most hours of daylight. That's usually on June 21st. It could be June 22nd as well sometimes, depends on the year, but it's usually June 21st. That's the day we get the most hours of daylight in the northern hemisphere. Right? December 21st is the winter solstice. That's the day where we get the least amount of daylight, fewest hours of daylight in the northern hemisphere. And then September 23rd, March 21st, those days are the equinoxes, equal nights. Those are the days where you get exactly 12 hours of daylight. No matter where you are in the world, you get 12 hours of daylight. And you can kind of see that over here, that like the November path, the December path is the shortest path. So that means the sun's going to be out for the least amount of time. Over here, the June path is the longest path. So that would mean the sun is going to be out for the longest amount of time. Because remember, the sun's going to move 15 degrees per hour across the sky, because what's actually happening is the sun's not moving. It just looks like it's moving because the earth is rotating. So the sun's going to move the same speed there as it is here, and this is a much shorter path, so the sun's going to be out for a smaller amount of time. This is a much longer path, so the sun's going to be out for a much longer amount of time. Shorter amount of time, longer amount of time. All right, lastly here, now if you look at the sun and you look at the size of the sun, what we find out is that the size varies in a cyclic manner. Now, how you describe the size of things in the sky, you don't just hold up a ruler and go, oh yeah, the sun looks 2 centimeters. How you describe the size of things in the sky is by describing its angular diameter. This how big the object looks measured as an angle. So for example, I mentioned before that each one of your fists is about a 10-degree angle, because if I hold one out, it takes 9 fists to get directly above. So each one of your fists is about a 10-degree angle. So if I saw an object in the sky and I held my fist up and it was about as big as my fist, it'd have an angular diameter of about 10 degrees. All right. Well, if my fist is 10 and it has 5 digits, 10 divided by 5 is 2. Each one of my fingers is about 2-degree angle. So if I looked up in the sky and I saw something about as wide as my finger, that'd be about a 2-degree angular diameter. If it was half the width of my finger, it'd be about a 1-degree angular diameter. All right, now there's fancy scientific equipment that's more accurate than just using my hand, but that's just to give you a rough idea. But anyways, so if you measure the angular diameter of the sun, what you notice is that it doesn't stay the same throughout the year. Sometimes of the year the sun looks bigger, other times of the year the sun looks smaller. And it actually looks the biggest in the wintertime and looks smaller in the summertime. Now the reason for that has to do with the shape of the orbit. Now, if the Earth traveled in a perfect circle around the sun, then we'd always be the same distance away from it and the sun would look the same size. However, the Earth does not travel in a perfect circle. The Earth travels in a shape called an ellipse, which is kind of like an oval. It's kind of like that, where sometimes the year we're over here, so the sun looks bigger. Other times of the year we're over here and the sun looks smaller. Now, the sun looks the biggest in the wintertime. We're actually closest to the sun in New York, northern hemisphere. We're actually closest to the sun in the wintertime. So what that tells you is our seasons are not determined by how close we are to the sun. What determines the seasons is the angle of the sun, which we'll talk more about in another day. But we're actually closest to the sun in the wintertime and farthest away in the summertime. That's not what causes the seasons. One little more thing I'll just point out real quick. Now, this diagram here represents New York State because we live in New York State and the tests are made for New York State. And this is the most common diagram you'll see for how the sun's path is. But that's not the sun's path everywhere. So what this diagram here shows you is the sun's path on June 21st at different latitudes. So see the New York path right there is basically the same as that. If you look at the equator, it doesn't really go up and down at an angle. It pretty much goes straight up and straight down. At the Tropic of Cancer, 23.5 degrees north, on June 21st, that's the day where the sun gets directly overhead. So you see that path has the sun get directly overhead and go down. Perhaps the most interesting one, though, is this one down here at the Arctic Circle, from the Arctic Circle going north. If you notice, all three of these have the sun rise and set, rise and set, rise and set. But in the Arctic Circle, the sun doesn't rise and set. The sun just kind of goes around in a circle in the sky. That's why if you live towards the North Pole, you get 24 hours of daylight in the summertime because the sun doesn't set. It'll get higher in the sky some parts of the day and lower in other parts of the day, but the sun is out the entire day. So it doesn't set at all there. All right, so that is the apparent motions of the sun.